Good evening, everyone. I am Renee Bodie, the General Manager of Soka Performing Arts Center. My preferred pronouns are she, her. Welcome to Astronomy Night with Dr. Bryan Penprase. Before we begin, I would like to recognize and acknowledge the Indigenous people of the land that Soka University and Soka Performing Arts Center reside on, the Ahachaman tribe. And while a land acknowledgement is not enough, it is an important social justice and decolonial practice that promotes Indigenous visibility and a reminder that we are on settled Indigenous land. Thank you for joining us for the first event of the Soka Performing Arts Center's new Expanding Horizons series. Soka Performing Arts Center sits on the beautiful campus of Soka University and features a 1,032-seat concert hall and a 400-seat black box theater. Our concert hall features acoustics by master acoustician Yasuhisa Toyota, who was responsible for the wonderful acoustics at Disney Hall and Suntory Hall in Tokyo, among many others. Our mission is to engage, educate, and elevate the human spirit. With this series, we hope to expand your horizons beyond the musical offerings that we have available. Please check out our website for our full range of virtual programming, including performances by great pianist Emmanuel Axe. And we have some wonderful wonderful interviews with jazz great Charles McPherson and many more. We are delighted to have Dr. Bryan Penprase, current Vice President for Sponsored Research and External Academic Relations at Soka University of America and the previous Dean of Faculty here at Soka. He previously was a professor of science and founding faculty member and director of the Teaching and Learning Center at Yale College in Singapore, and served as an American Council on Education Fellow at Yale University in 2012 to 2013. Bryan served for 20 years as a professor of physics and astronomy at Pomona College, where he served as a department chair and was the inaugural co-director for the Liberal Arts Consortium for Online Learning. Bryan received both a BS in physics and an MS in applied physics from Stanford University in 1985 and a PhD from the University of Chicago in astronomy and astrophysics in 1992. Bryan's research includes nearly all aspects of observational astrophysics, using telescopes such as the Hubble Space Telescope and the Keck Telescope in Hawaii. He is the author of 2 books, which includes STEM Education for the 21st Century and the Power of Stars, How Celestial Observations Have Shaped Civilization, both published by Springer Incorporated. Bryan has lectured across the world and has taught a wide range of courses in archaeoastronomy, astronomy, physics, and astrophysics. He has led expeditions to study the astronomy of Native American groups across the southwestern United States, as well as numerous solar eclipse expeditions. Bryan has co-authored and authored over 55 peer-reviewed research articles in Nature and Science and other publications. His most recent research program is a collaboration with Caltech to develop the Zwicky Transient Facility and a global relay of observatories known as Growth, electronic for studying gamma ray bursts, new supernovas, and the electromagnetic counterparts of gravitational wave force. We are honored to have him with us. For tonight's presentation, we will be using the Q&A format. So if you have a question for Dr. Penprase, please click on the Q&A icon at the bottom of your Zoom screen and type your question in the box. We will try to get to as many questions as we can. Please join me in welcoming Dr. Bryan Penprase.
Hello, everyone. Ordinarily, I'd be hearing thunderous applause right now, and I'm really grateful to Renee for such a kind introduction. But actually, I'm standing right in front of our observatory, the Nieves Observatory here at Soka University of America, in what really is an empty campus. There are just deer and a few cars parked around here. Our campus has been in a mode of remote instruction. And so we've been managing through the pandemic by offering the best type of instruction we can for our students using online technologies. And one of the technologies that we have now available to us is this wonderful observatory that we'll be seeing more of tonight. And so I thought it would be fun to share with you some of the capabilities of our observatory, take some images of the moon, Mars, some nebulae, and share that with you in what I used to call a star party. So this is a virtual star party. And the astronomy night that we're doing is one of, we're hoping, a new series of online events that will really allow us to reach out to the community, engage in new ways. One of the happy surprises about having a telescope like this, which can be operated from anywhere in the world, is that our students who come from all over the world, from over 40 different countries, can operate this telescope. And so I've been working with my students as they've been in Nepal, India, Japan, Hong Kong, all across the US, and all of them have been operating this telescope and taking beautiful images with it and working together, collaborating on their astronomy projects. It's really been a fantastic resource. And I'm very grateful to Nieves for making it possible. We call it the Nieves Observatory after him. And it's just one of the many new capabilities that we're getting here at Soka University for sciences. We're opening a new concentration. This is our first year of our life sciences concentration and our new Curie Hall, a 91,000 foot science building. So we hope we'll see you all on campus soon, and you'll be able to see some of the wonderful science and other cultural events that we have here on our campus. One other point I'd like to make before we go into the telescope is our mission here at Soka University is to promote global citizenship. And I always like to make the point that as an astronomer, that's what we're all about, because when you're looking into the heavens and seeing planets and stars and other galaxies, it really underlines the fact that we all live on one very small, tiny planet. And so not only can we make global citizens out of this astronomy instruction plan here, we can also make interplanetary and intergalactic citizens. And I really enjoy sharing the skies with the students and with you. So thank you for coming. So what we'll do is I'm going to go inside the telescope and open up the dome. And I'm being assisted by my student, Daniel, who's located at his home, hundreds of miles away. Daniel, I'm going to just turn it over to you to introduce yourself while I go into the dome, and then we'll open up the dome.
Thank you, Dr. Penprase. So my name is Daniel. I'm currently a senior at Soka University. So I was lucky enough as a student to attend one of Dr. Penprase's classes on astronomy. This was really not my concentration or really what I was focusing on, but I really thought it'd be an interesting class, especially since we just came from study abroad. And you can very clearly see the difference from to the skies from different places around the world. So I thought I'd give it a shot, and it really astounded me. And with the help of the telescope, we were able to see a little bit of everything that's out there, the vastness that is space. So currently I am doing a capstone, which is basically my senior thesis, and with the help of the telescope and Dr. Penprase to be able to see if there's planets in other star systems very far away from us. So our telescope is, even though it might be a little small compared to the big telescopes that NASA uses, we can still see light that has been traveling for tens or hundreds of years at the speed of light, really get all of these photons in our telescope. And it's just been very, very impressive. Here, what I like about Soka is that we can do a wide range of things, and something that I would have never thought would be have such a big impact in my life really turned it around. So I want to thank Soka and Dr. Penprase for that.
Well, we're grateful to you, Daniel, and thanks for helping out tonight. So as we're doing this program, we're going to sort of mix in live images from the telescope, a little bit of astronomy talk, and the latest information about the new JPL mission. And one interesting aspect about planetary exploration, just like a lot of things today, is a very global effort. And right now on Mars, there are several different missions that have arrived, and on the moon as well. If we see the moon from Earth, we can see the very familiar maria, those smooth dark areas that together form a shape on the surface of the moon. The moon rotates once every orbit, so we only see the same side of the moon all the time. Various cultures around the world have described the shape of the maria as a rabbit. or other things, but a rabbit is one of the more common interpretations from Asia. And in China, the rabbit is actually the mythological character of Yutu, who helped the princess Chang'e in her journey to the moon after she gathered the elixir of immortality. And the Chinese are also exploring the moon. They've launched 5 different Chang'e spacecraft, 2 of which had rovers and 1 of which has done a sample return mission. And so when we look at the moon, we're looking at not an empty place, but a place that has several different nations' spacecraft that have visited. And soon Mars will be in that same category. The moon right now is in a waxing phase. It's approaching first quarter. So if you're an astronomer, you do not call it a half moon, you call it first quarter moon. I always make my students understand that. And the moon, as it orbits us over its period of 29.5 days, shows a slightly increasing amount of illumination each day. That's the waxing part of it, as we spin underneath it. And one of the other amazing things I always try to get my students to remember is that everything's moving in the universe. We're spinning, we're orbiting, the sun itself is moving. All of this motion is part of the cosmic energy that sort of connects all of us, all the planets, all the stars. It's a very dynamic universe out there. And one of the things that we've been able to do as a species is reach the moon, as our human astronauts have been on the surface. And one of the most profound realizations that comes from that is the view back of Earth. As when you see Earth suspended in space, you realize how small, how fragile, and really how insignificant the differences are between people and between nations. And so our Earth is really, when you study space and you study the universe, it brings you right back to Earth, and it makes you appreciate Earth and our human civilization even more. So that's a little bit on the moon, and you can see it's in this waxing phase right now. A little bit about the Chinese rovers, which have been on the surface. One of the more interesting aspects about the Chinese lunar program is that they've also been able to land and rove on the far side of the moon. And in the process of getting over there, they were able to take pictures of the far side of the moon, which is only the 3rd nation that's done that. The Russians and the Americans have also done that. And they've also managed to land and return a sample with the Chang'e 5 spacecraft. And here's the picture that you see of the moon from the other side. And so despite all of you who are Pink Floyd fans, there is no dark side of the moon. There's only the far side of the moon. And this is what it looks like with the Earth sitting next to it. So these are pictures of the Earth as a waxing crescent, as viewed from the Chang'e spacecraft. And this is Earth from even farther away, a tiny little blue dot. And I also just want to share that famous quote from Carl Sagan, who's one of my heroes, who was involved in the 1970s mission where Voyager reached out to the edge of the solar system and looked back. And as it looked back, it captured this image, the pale blue dot image of our planetary home. And as Carl Sagan put it, he said, "That's here, that's home, that's us. On it is everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, who lived out their lives." And this is actually something, again, that comes to you when you study astronomy, is a sense of how we're all interconnected. So I'm going to switch a little bit now and jump onto our telescope, and we're going to look at some live images of the moon from our telescope. And for that, I'm going to have to move into our telescope view, and I'm having trouble. Oh, I see what I'm doing. Okay, got it. I'm going to stop sharing. And then if we could highlight the space view, I'm going to actually give you a chance to look through the eyepiece of our telescope virtually. So while you're all nice and warm and sitting wherever you are, I'm out here in the cold dome. But I'm able to, through the magic of technology, give you a view through our eyepiece. So I have my phone actually attached to the eyepiece, and I can actually move the telescope to actually scan across the lunar disk a little bit. And so I'm going to just open up our telescope control program, and I'm going to move the telescope just a little bit. Okay, there we go. It's getting a little bit feisty. And so you can see this is a live image of the moon from our telescope. And this is at sort of medium magnification. It's looking through our visual system. We have two telescopes here that are hooked together. If we can actually get the telescope view for just a second, we can spotlight the telescope view. We'll be able to see how we have a pair of telescopes hooked together. And the reason why we did that is the large telescope on the right is used for our students who are doing advanced imaging projects like Daniel. And it has a very large and very fantastic research grade camera on the back of it. And then the little telescope on the left is so we can look through it. And so that's where we're seeing right now this live view of the moon. And you can see this beautiful region in the terminator where the moon has all of these craters beautifully highlighted with their shadows revealing the terrain that's visible there. So now I'm going to ask Daniel to actually take a picture through our main telescope camera. So he's moving it just a little bit, and we'll see in our main research camera what the moon looks like. And on the back of our telescope is a camera that is what we call a CCD, charge coupled device camera. And it has a set of filters. So we can take images through different colored sheets of glass in red, green, blue, or also in very narrow filters that isolate lines of hydrogen, oxygen, sulfur. So this allows us to do a lot of different kinds of research projects with the telescope. So Daniel, it looks like you got a nice image there. Shall I share that with everyone?
Sure, please, Professor.
Okay, so I'm going to just share the image that Daniel just took with everyone. I'm going to share over here. And this is a live image that we took with our camera. And if we can sort of pan around a little bit on it, we can actually see in one image a big part of the moon's surface. And Daniel, did you recenter the moon here in this image?
I did, but I'm gonna move it just a little bit.
Okay. Well, what we'll do is we'll just move it a little bit on the telescope, and we'll take a new image. And when we get this image, we can actually zoom in on it, and we can adjust how we shade the image as well in what's called a screen stretch. So we can actually isolate different levels of illumination and highlight some of the craters and study them. One of the exercises I had my students do in our learning cluster in January was to take a crater and use the image to actually measure how big the crater is, identify which crater we're looking at, and then imagine yourself on that crater looking back at Earth, and to actually figure out what the Earth would look like, what phase the Earth would be in, and how the Earth and Sun would appear to move for you if you were on the moon at that spot. And the students really enjoyed doing that. And this is something I also do when I teach. I joke about it, cultivating a sense of interplanetary empathy, that you can actually imagine all of these celestial objects as places that you might visit at some point. Okay, so let's see. So I'm going to then stop the screen share here. And I think, Daniel, are you going to take another moon image, or
I will
talk a little bit about Mars? Okay.
Hopefully.
So it should just go. If you hit go to on moon, it'll just go to it. Yeah, that's it. Okay. So while Daniel's getting that ready, we don't need to watch the space view at this point because we're centering it on the other camera. Oh, there we go. That's it. So Daniel's got a really nice image here that I want to share with you guys. So I'm going to share the latest image. And this one is quite nice. And it features a nice centered view of the moon with a great exposure. And you can actually adjust, again, with the screen stretch, which part of the moon that you want to focus on. And you can zoom up on it a little bit and see a lot of detail. So this camera that we have sees about 47 arc minutes of the sky. The moon itself is about half a degree. And we can use it to take pictures of galaxies and nebulae, which we'll do a little bit later. Okay, so that's our little moon viewing exercise. I think now we're going to switch gears a little bit and talk a bit about Mars. And so while I start doing that Daniel, if you want to move over to Mars, and we'll actually look at the telescope view for a moment. You can see the telescope moving a little bit. Right now, Mars is sitting right next to the moon, and you can actually find Mars just by looking to the little red dot sitting next to the moon. They're both in the same part of the sky. Mars, instead of being about 1 light second away, which is how far the moon is away, is actually about 11 light minutes away. And in astronomy, we measure distances with these kind of light minutes, hours, or years. The sun, by the way, is about 8 light minutes away. And so that's what we call the astronomical unit. So I'm going to just talk a little bit about Mars while Daniel is taking some images. So I'm going to go to some slides here that we have of Mars, and we'll also get to a point where we can talk a little bit about that amazing mission that landed there today. So as you probably know, and most kids who go through their astronomy phase know, all the different planets have characteristics. The Earth, Venus, Mercury, and Mars are what are sometimes called terrestrial planets. And Mars is about half the size of Earth in diameter and about 10% of Earth in mass. It has a very thin atmosphere, about 1% of Earth's atmosphere. And it has a day that's almost exactly the same as Earth's day length. It's, instead of being 24 hours, it's 24 hours and 39 minutes. And that's what in the JPL business they call a sol, which is the time for the sun to make one apparent rotation. Other interesting thing about Mars is it has an atmosphere of carbon dioxide, which it's so cold that it often freezes into dry ice. And that's what the polar caps are, is dry ice. And it has a really interesting surface that features the largest mountains in the solar system, including Olympus Mons, which is fully 3 times larger than Earth's largest mountain in the Himalayas, Mount Everest. It has the universe's largest canyon system, the Valles Marineris. And that can be seen very easily in this color image here, which shows all of the different parts of Mars in this sort of color that indicates the low altitude parts of Mars in blue. And one interesting thing about Mars too is its history indicates that about 3 billion years ago, it was filled with water. We can see evidence of large lakes, river systems, perhaps even oceans. And so when the solar system started out around 4.5 billion years ago, Mars had oceans and lots of water, which makes it very, very likely that at some point life could have arisen on Mars. And that's one reason why there's so much interest in this planet. It also has seasons, much like the Earth, in that the spin of Mars is tilted away from the sun for half of its year and then toward the sun for the other half of the year. And that causes its ice caps to actually melt and evaporate depending on the seasons. Okay, so those are some interesting facts about Mars. Now, JPL has been launching rovers to Mars for many years, the first being the Viking lander in 1976, the first rover being this tiny little rover here in the bottom, which is so small that when my kids were small, my wife and I used to work at JPL, we could actually, for an open house, they would bring out a model of this thing. And for fun, they would have it sort of drive over all the kids because it's only like the size of a little kind of toy. But this was a proof of concept that grew into the larger rovers that are sitting next to it. And the most recent rovers are like small cars that are able to drive many kilometers on the surface. So JPL has steadily been improving these rovers and also adding new ways of getting them to the surface. And the first way that they would land would be to deploy these giant airbags, which would inflate. And then the spacecraft would come zooming into the atmosphere, release a parachute, cut off the parachute, and then deploy these airbags and allow it to crash onto the surface and bounce. And it would bounce as high as a 10-story building. Inside this airbag is an incredibly sophisticated, expensive, delicate scientific instrument crashing onto the surface and bouncing many times until it comes to a stop and somehow surviving. It would open up itself and drive around. And that was how these first of the rovers worked. Now, the most recent rover that has been launched is the Perseverance. And I'm going to pause a little bit and I'm going to go back to our telescope because I think, Daniel, do you have a Mars image that you can show for us? It's a little bright.
It seems to be a little bright.
Yeah, that's okay. So I'm going to just switch briefly to our live Mars image here. And before we talk about the rover. And so I'm going to go over to our telescope computer and I'm going to share the image that Dan just took of Mars. So there it is. Now, this image is obviously not a Hubble Space Telescope kind of image. It is actually, Mars is this little circle here in the middle with the little spikes from diffraction. If it were a color image, it would be a little red dot. This is a science camera that takes only gray images. And like a lot of science cameras, it only measures light intensity. It doesn't have built-in color. So we actually can construct a color image. So if we took a red image, a green image, and a blue image, we could mix those together to get color. But from this image, you can actually see that it's not a star, that it actually has a certain width to it. And again, this is an object that is so far away that it looks like a little star in the sky, even though it's many times bigger than the moon, but it's so much farther away that it recedes into the sky to be a tiny little dot. Okay, so let's talk more about the exploration missions. I'm going to show you some of the videos from the JPL mission team of the most recent rovers, which is the Perseverance. And one of my favorite videos on that, I'll get that for you guys. Okay, where did I put it? Oh, I see, it's on. Okay, hang on a second. Okay, I gotta do that. That's the problem with this. Okay, let me share the video here. Okay, there we go. So this video I really enjoy because what it shows you is what it would be like to fly along with the Mars mission as it gets to the deployment. And so I'll just play it here. It's almost as if you're on board with it. Okay, so as it's traveling through space, it takes it several months to reach out to Mars. This is one reason, by the way, that the Chinese, the United Arab Emirates, and the US missions are all arriving basically this week at Mars. There are what are called launch windows where it's favorable to be to Mars. So as it travels through space, it eventually gets close enough where it can release some of the hardware that it used to adjust its course heading to Mars. And the amount of precision here is fantastic. If this were a target that it's trying to hit, which is a tiny little window in the atmosphere, if it goes too low, it burns up. If it goes too high, it bounces off. And then what happens is when it gets there, it begins to use the very thin atmosphere to slow it down. It slows it down enough so that it can deploy these parachutes. And then the parachutes then allow it to reach a reasonable enough velocity so that it can then control its descent with little rocket motors. And all of this technology has to work perfectly. It's been sent off for almost a year through cold interstellar space. But the most amazing part happens next. After it gets a little closer to the surface, it releases itself and becomes a free-flying rocket-powered spacecraft. And it hovers over the surface with sensors measuring the exact place where it can then land its rover. And these rockets are precisely controlling its position. It's using its own autonomous computer sensors and capabilities to figure out where to land. And one of the problems here, they're looking in Jezero crater, which is a area on Mars's surface about the size of Lake Tahoe that at one time was probably a lake. They cut the cables, the rockets fly off, and there it is. The rover is ready to work. And this is what happened today. This whole sequence of events happened at lunchtime today, about 12:55 p.m. And amazingly, every one of those systems worked perfectly. And the things that could have gone wrong are a very long list. It could have landed on a giant boulder. It could have had any number of hardware failures. And one of the other amazing things that happens is there's an 11-minute delay between the events on the surface of Mars and here because of the speed of light. So the other thing that happens is when they're getting these signals, they don't know if the spacecraft has already died on the surface many minutes ago. I think this is a time when we can show that video that the mission controllers had in their control room, and I'm not sure if we have that one queued up. Do we have it? When it landed, it took this really nice image though of the surface. Oh, there you go. Are you doing this, Daniel? Yeah. So Daniel's going to show us the actual live feed from JPL.
6.6 kilometers of the surface of Mars.
Again, all these events were happening on Mars.
Continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
And so there's this 11-minute delay, so it could have already crashed
We have
and been dead on
confirmation
the
that the
surface,
lander
but they
vision
wouldn't
system has
know.
produced a valid solution and part of terrain relative navigation.
And that's the computers automatically finding where to land. And it makes the best decision of where to land all by itself.
Current
The mission
velocity
controllers
is
can't really
82
steer it.
meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
Oh.
We have
This was the
completed
scene
our
today.
terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
There's a very tense moment here as they just don't know what's going to happen. They're all very quiet.
We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct
And the sky crane is the cables that lower it down to the surface. Again, they're very quiet because they're quite nervous.
Started about 20 meters off the surface.
Quiet, tense.
We're getting signals from MRO.
MRO is the Mars Reconnaissance Orbiter. It's in orbit, and it's monitoring the mission more locally.
Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And that is just an awesome scene. So thanks, Daniel. We can go back. And I think at this point, Daniel, if you want to point the telescope at some other object, like maybe the Orion Nebula, I think that would be a nice thing to work on. And I'll just try to keep the camera from getting tangled up when you move it over there.
Okay, perfect. So
And what I'm going to do is actually show a few more images here while Daniel's getting that set up. And then we'll, after that, open it up for questions. So the actual first image that was taken was of the surface of Mars, a gray science type of image. And the cameras on this rover, there are over almost 30 of them, will be taking fantastic color images and detailed spectroscopic analysis of the surface will happen. It will drill cores of rock for later recovery. And it also has a little helicopter on board. Isn't that an amazing thing, a Mars helicopter? So it's going to drive off to a relatively flat spot and launch this little helicopter, which is called Ingenuity, in probably about a month. And it'll also drive around looking for evidence of life on the surface. It has an interesting device on its suite of instruments known as MOXIE, which is an oxygen removal technology. So they can actually take carbon dioxide from Mars's atmosphere and produce oxygen with it. And so these are just some of the amazing technologies that are going to be deployed on the Perseverance rover. But lest we think that everything centers around the Americans, I think it's important to point out that we're not the only ones out there. In fact, in the case of Mars, there are 3 different nations that are landing spacecraft, or at least arriving to the region of Mars. And one of them is the Chinese mission called Tianwen, which is sort of 2 different spacecraft that will be one orbiter that's currently now in orbit around Mars and looking for the best landing spot. And then they're going to release the lander once they've mapped out the surface. And this one arrived on Mars on February 10th. And then the United Arab Emirates also has launched a mission to Mars. And this mission they call Hope. And it's designed to do something that none of the other spacecraft up there are able to do, which is take regular images of the entire surface of Mars. And this can be used for monitoring the weather, for dust storms, and for other kind of large scale changes on Mars. So these are some of the missions that are going on right now, and all 3 of them have come up to Mars at the same time, which is really an amazing event. And it highlights the international nature of astronomy and space exploration. And that, just like astronomy promotes this sense of being all part of the same planet, I think space exploration does that as well. And so I think it's a wonderful way to kind of feel that sense of common humanity. We all look up at the sky and wonder what's up there and what's it all made of and how do we all fit in. So that's about it for my talk. I think I would like at this point maybe to have a few questions, which I'd be happy to answer.
We can move the telescope and send it over to
yeah.
M42 if
okay. So while I'm answering questions, Daniel's going to be playing with the telescope and taking some images of different things. So I'm going to just have a look at some of these objects too as we go along here. So right now he's going off to look at the Orion Nebula, which is a really beautiful object in the sky, about 1,500 light years away. So a little farther away than the Moon and Mars. And so again, while I'm answering questions, Daniel's taking a picture, and I'll share that with you guys in just a second.
So Brian, your first question that we have received is, what is the temperature of Mars?
Yeah, so it ranges quite a bit. It can be as cold as around minus 100 or so, and as hot in a hot summer Martian day as plus 80 Fahrenheit. So one of the fun things that both of my kids live in Minnesota, and so on a really cold day in Minnesota, they'll actually check, because they're my kids, they know how to check the temperature on Mars, and they'll say, hey, it's colder here in Minnesota than on Mars. Generally, the temperatures are sort of, colder than any point on Earth, around a minus 100, minus 110 or so. But like I said, during the hot Martian summer, if you're on the equator, it can actually get up to plus 80 in direct sunlight. Wow. Average temperature is below freezing.
Amazing. So the next question is, do you think it is possible to determine the composition of ancient Martian atmosphere by drilling core samples from the Martian poles and/or glaciers?
Yes, this is a great question. And it's something that's been done on Earth. And these ice cores that we have give us a perfect record of the ancient climate by way of little bubbles of gas that are trapped within the ice. So when you take ice cores of glaciers on Earth and Antarctica, you can drill very deep inside and find bubbles that are trapped samples of the Earth's atmosphere from hundreds of thousands of years ago. So the hope would be that if you could drill into some of the dry ice up in the Martian poles, you might be able to get some of that. But one of the complications is that the temperature range on Mars is so extreme, and the ice that's there is mostly carbon dioxide ice. You wouldn't really be able to have the same stability as you would with an ice cap made of water ice. And in fact, in some years, the ice caps on Mars evaporate almost completely. So the trick would be to find some kind of stable geologic region, some kind of maybe under the surface ice that could trap some of those little bubbles that could give you that sample. And so some of the most promising future Mars explorations involve this idea of drilling under the surface, looking for subsurface water, subsurface life. That was one of the purposes too of the InSight mission, which is the US mission that landed before this one. And it was intended to drill deep into the surface of Mars to look at some of the subsurface characteristics.
Great. So the next one is, how was Soka chosen as a location for an observatory? Most observatories are placed away from light pollution.
Huh. Okay, well, I don't know if that person has actually visited our lovely campus here up in the hills. We're in this beautiful location, and wrapping around our campus is this beautiful Orange County Park, a Wood Canyon Preserve. So we have actually very little light all the way around us from this park. The only inhabitants of this park are deer and other creatures. There are a few humans living up on the ridge above us, but the whole half of the sky facing toward the ocean from here is really dark. So we have a pretty dark site in most respects. We have a lot of moisture here, though. That's one issue, because the Pacific Ocean is just 3 or 4 miles by air from our campus. So we do often get layers of cloud coming in. But all in all, it's a pretty good site. And we've been getting some spectacular images, which I think Daniel will be able to show us some of the images he's taken from here in a little bit.
Oh.
Daniel, are you ready for image show and tell?
So we have 20 seconds if you want to share the screen to see as it pops up, and we can also see some of the pictures that have been taken before on this specific telescope.
Okay, so we're going to pause just a moment. Daniel's taking a live image right now of the Orion Nebula, and do you want to just actually stretch that one and I'll share it?
Sure.
No, that's beautiful. So I'm going to share Daniel's work right now. This, by the way, is another amazing thing about the world we live in right now. I can be here in this part of California. Daniel lives sort of near San Diego. I can have a student in Japan, another student in India, and all of them can work together online in this way. So I'm going to just shift over to our screen. And Daniel just took this really beautiful image here of the Orion Nebula while I was answering questions. Daniel, you want to sort of zoom in and kind of play around with the stretch for everyone?
Sure. So this is how it would come out at the very beginning. And because it takes all amount of light, we kind of want to select the exact light that we want. And then we play around with it just a little bit and can really see all of the different things that it brought up. And this is just from our small little telescope.
That's amazing, just a few minutes. And what this is a colossal star forming region in what amounts to the nearest giant molecular cloud to us. There are literally hundreds of stars forming inside those gas clouds, and they're being lit up from the inside by the stars. After they turn on, they begin to evaporate and illuminate the clouds that form them. Just amazing. And then I think, Daniel, you have another image that you took a little while ago. Is that right?
Yes, and this is actually, I think we need to stop the share and make the new share.
Let me do that. I'll happily share that because I'm sitting here on the computer. Photos?
And this was taken by actually me a little while ago. But this is what, based on the different filters, so we combine different gases that we see in this object, and then we take the different pictures and then overlap them together, and then we would get something close to what we would see if we could see something of like gases or whatnot. So this is fake color, but because we're looking at gases, so it's not something you would see, but we can see all of these beautiful ranges of color as it goes in there.
Yeah, and these are taken with 3 different what we call nebular filters. There's one for H alpha, which is hydrogen emission. There's one for oxygen, and there's one for sulfur. So we're able to tune into the atoms, 3 different atoms, and mix them together. Thanks, Daniel. I think what we're going to do next is take some more questions. And then, Daniel, you want to take a picture of a galaxy for us?
Sure.
So your next question is, what are the magnifications of the 2 Soka telescopes?
Yeah, that's a good question. As you can see, we can get a lot of detail with our camera here. The camera is able to image a region of the sky that's a little more than ½ a degree in size, about 47 arc minutes, at a scale of about 0.7 arc seconds per pixel. That doesn't translate directly to a magnification because we're not looking with our eyes. And so if we were looking with our little telescope with our eyes, then we get a magnification that would be calculated based on the ratio of the telescope focal length to the eyepiece focal length. And so in this case, we can get anywhere between a magnification of 140 to about 300 with our little telescope for visual observing.
Amazing. So the next question.
The telescope. Yes.
How far will Perseverance travel, and how are samples transported back to Earth?
Yeah, that's a good question. I have their press kit here with me in the telescope. And, you know, a lot of times they have a nominal mission life that becomes much greater by the time the mission is over. So what they're planning is to have it rove around this Jezero crater, which in size is about the same size as Lake Tahoe. So that means, you know, maybe about 20 or so miles. They're going to study very thoroughly. But like most of these JPL missions, it's probably going to live a lot longer than this nominal mission. So they can actually plan some interesting longer journeys for it as it goes beyond its first year. And so we'll just have to wait and see what it ends up doing. But the earlier rovers ended up traveling 10 or even 20 times farther than the nominal mission by the end of the spacecraft mission.
Wow. So the next one, is there a specific focus of Soka astronomy projects?
Well, okay, so we have one astronomy professor here at Soka, that's me. So in terms of Soka astronomy projects, the way I like to describe my research is I do everything from asteroids to quasars. And if I had some other objects after Q in the alphabet, I would add them. So I study asteroids, I study supernovae, I study extrasolar planets. I generally will do almost anything my students are interested in. But most of my research that I've been spending the most amount of time on recently involve this project that you mentioned at the beginning, Renee, the Caltech project looking for transients. This is a really interesting new field, and even a little telescope like this one can contribute because there are all kinds of things blowing up in the sky. There's supernovae, there are novae, there are gamma ray bursts, there are gravitational lens events. All of these things can be captured, even with a little telescope, if you just happen to be looking in the right place at the right time. So in conjunction with some of the astronomers at Caltech and our global network, we can actually work together internationally to capture the light from a star that's dying or from a black hole that's being formed. And so I'm really excited about that kind of research, and I'm hoping our little telescope can contribute in studying some of the new objects that are being discovered from these larger telescopes at Caltech and some of the other major observatories.
Well, that kind of segues into the next question, actually, which is how much sharing happens between countries?
You mean in astronomy?
Yes. Well, I'm assuming
Yeah.
they're asking astronomy.
Yeah, so this is one of the most wonderful aspects about astronomy and science in general, is that it is such a great unifier of people. You only really want to know what nature is doing. You want to find out truth. And people in science work together, they collaborate, they share data, and you have a common interest if you're a scientist that very few people in the world share. So it immediately brings people together who might come from different parts of the world, might speak different languages. And so I found that to be just a wonderful thing. If, for example, at one point, the biggest, most important thing in my life was quasar absorption line spectroscopy. Now, how many people do you know who are excited and fascinated by quasar absorption line spectroscopy? Well, believe it or not, if you look all around the world, there's probably a community of around 300 quasar absorption line spectroscopists. And when we get together, it's like, wow, we're like best friends, no matter where they're from. They can be from India or China or anywhere. And we just like, we can talk quasars. And that's a fantastic thing to have that common interest. It brings everyone together.
That's
And most of the
incredible.
major telescopes are international projects. When I was a graduate student, I used telescopes from the European Southern Observatory, and they had literally about 15 different nationalities represented in the astronomers on the mountain at any given time. It's just such a wonderful mixing of cultures and people.
Beautiful. So the next question is, how will Mars become more relevant in our lives as technology advances? And when do you see that happening?
I think, you know, space in general is getting more relevant in our lives. And every time you use a cell phone, you're taking advantage of space technology. There are any number of satellites that are beaming coordinates to you through your GPS location services. There are any number of other advanced technologies in that phone. And space is being used more and more for boosting our agricultural productivity by monitoring fields and rainfall and other things. So I think space is becoming more important, and Mars, as part of that global effort for exploring the universe, will become a kind of a gathering place, just as it has this month, of all the different spacefaring nations. So India, Russia, the US, China, United Arab Emirates have all been sent spacecraft to Mars. And I think this is a great avenue for international cooperation. Just like the South Pole and the Antarctic research has also been a very international project. I do hope that whatever we do with Mars, it's done in a cooperative, collaborative kind of way, and with an eye toward preserving and sharing whatever we learn with all the people in the world. And that's certainly the case for NASA and its approach to space exploration. All of the images from this lander are going to be sent around the world and made available to people very quickly.
Wow. So the next question is, we've had a number of rovers on Mars, including the amazing Curiosity, but finding any sign that there was life on Mars has been elusive. What is different about Perseverance that might improve the chances that we can find ancient life?
Yeah, that's a good question too. And it has a more advanced instrument set, and it's what kind of just like real estate. It's location, location, location. So this Jezero crater that they've landed it on is almost a perfect location to look for life. It sits at the base of an ancient delta system. So it would have been fed from a primordial river a couple of billion years ago for many, many millions of years. And so it probably has sediments that, if there was life, would be rich with evidence in the form of little microfossils or other kind of signatures of life. So I think more than anything, it's just the fact that they were able to land it so precisely in the middle of this crater. And the crater is important because it digs up some of the edges of this delta system, so they can actually look at a profile of rocks that would have been deposited over a long period of time. So Curiosity also had that feature where it could actually climb up a series of strata and read the geologic history of Mars as it climbed up. And this one as well will be able to look around in the crater and see evidence of different epochs of Martian history, and hopefully also some evidence of maybe some little microfossils or other minerals that could have come from life.
Oh. So this question has been asked more than once. What happens to the rovers after they die? Are they just left on Mars?
Yeah, so they become space junk, and this is not a major environmental hazard at this point, but could become one if our rate of exploration continues as it has. So I think there's they just sort of sit on the surface. There's no kind of recycling effort yet. I suppose there'll be a nice souvenir for someone later on once we get more people going off to Mars.
So the next one is, I'm very curious about the effect Mars has on Earth. We know how the moon affects Earth. Are the Martian influences on tides and weather pretty much the same, even at such a great distance?
Yeah, so the quick answer there is no, because it is so far away. Even though it's a much more massive object than the moon, the gravitational effects fall off as distance squared. So if you sort of compare 1 light second, which is the moon's distance, to 11 minutes, which is Mars's distance right now. So you're talking 11 times 60, right, which is about 600. So it's about a factor of 600 farther away. So the gravitational force is 1/600 squared, which means it's maybe like 1/1,000,000th as much force as you would get from the moon. So even though it's a larger object, because gravity falls off so quickly with distance, it wouldn't affect us at all in terms of the tides. And this is what some people have actually used to argue against astrology, in that there is no force from planets. And so it's an interesting idea to think that planets are able to affect us, but there's no scientific basis for finding that mechanism.
So the next one is sort of a two-parter. What is the confidence that the liquid on Mars was water? And if there was water on Mars, how did it dry up?
Okay, that's a great question. So when you look around and you see all this evidence in the form of, rivers and deltas and other, it looks like there was water. But the question is asking, so, well, okay, but how do we know it was water? And water is, of course, one of the most common molecules in the universe. If you look around, the most abundant molecule in the universe is molecular hydrogen. In the solar system, very simple compounds that have hydrogens in it, because hydrogen is the most common atom, are the most common molecules. So you've got hydrogen attached to carbons, that would be methane. Lots of methane found in the outer solar system. You have hydrogens attached to oxygen, that's water. That's really common. You have you have combinations of hydrogen and carbon and oxygen are the most common molecules. So in the case of the inner solar system, we have lots of water vapor in Venus, we have lots of water on Earth, and it's the way that the sun formed, it was able to evaporate a lot of elements and send them out to the outer solar system. So a lot of the lighter, sort of more volatile elements, and that would include the methane, got pushed out to the outer solar system. But here in the inner solar system, like Earth and Mars, the water, which was a little harder to melt and a little harder to evaporate and transport, stuck around. And so the thought is, in the early solar system, Earth, Venus, and Mars were just soaked with water. They had a huge component of water. And again, there's evidence in the fossil record, certainly from Earth, there's evidence from the atmosphere of Venus, and there's evidence from all of the erosional features on Mars. So the question is, what happened to that atmosphere? What happens to all that water? And it actually works out that because of the fact that Mars has such puny gravity, that when you get that Martian summer, when it gets really hot and everyone wants to go to the Martian beach, the sunlight is hitting those little water molecules and creating little Martian water vapor clouds. But the gravity on Mars is so weak that those clouds of water vapor have the chance of actually escaping the planet. And it takes a long time. It's what the astronomers sometimes call a planetary air leak. But planets that have low gravities, like Mars, have a hard time hanging on to certain parts of their atmosphere, and water eventually leaks away from a little planet like Mars. And so that's what happened. It just didn't have enough gravity to hang on to it. So when the astronomers are talking about Earth-like planets, they look for a planet that has enough heft to be able to hang on to the water, enough mass. Because for life to exist stably on a planet, at least life that we know of, water-based life, you have to have a large enough mass to retain that water for a long time. And Mars just didn't have the gravity.
Well, then that
I always have my
segues into.
students calculate. Go ahead.
Go ahead. You go ahead and finish. Is it?
Oh, it's just one of the things we do in our class that I like to have students think about what the escape velocity, which is set by the mass and radius of a planet, and all the atmosphere that we have on our planet is moving. All the molecules of oxygen and nitrogen that we're breathing are zipping around. As long as they're not moving faster than the escape velocity, they stay. But as soon as one of them gets moving faster, on Earth it's 11 kilometers per second, that molecule is off in space. But thankfully, we're at a temperature that's low enough that most of those atoms and molecules are happily kept around for a long time.
So that kind of, it's part and parcel to this one, which is, given the extreme temperature on Mars, what type of life form might one expect to find on the planet?
Yeah, so when it was a younger planet, it would have lots of water and presumably also atmosphere, and that would actually create a less extreme range of temperatures. So we enjoy on Earth the wonderful blanketing effects of our atmosphere, which cause us to have fewer extremes and swings of temperature. So it is quite likely that there's probably about 1 billion years of Martian history where there was plenty of water and plenty of atmosphere. And so, if life is possible on Earth, it might also have arisen on Mars, might have been the same kind of creatures we had in the first billion years of life on our planet. We can't really assume that all planets would have developed like Earth, but if it did, we'd expect a lot of these sort of microbial types of life in huge Martian oceans, and they would leave behind evidence of that and maybe fossilized, beds underneath some of the layers that this mission that's there now will be digging into.
Wonderful. So I love this question, and this we can, it's 8:30, so we could make this the last question unless you still want to keep going, Brian. But here is this: is this webinar something new? Will there be more webinars, Zoom meetings like this? And you can answer, and then I can also add to that. Go ahead.
Yeah, I think the answer is yes, this is something new. Although, all of us have been teaching online now for a long time. And so we're getting better at it, I think. And I would love to see us do more of this, but I would like to ask Renee if this is part of our plan.
Absolutely. I'm very excited about this new Expanding Horizons series. And I think it's definitely obvious from the immense interest that it's a good thing for us to do, and to highlight what our faculty is doing and learning, and being able to expand everyone's ability and knowledge is just phenomenal. So I'm excited about it. Yes, the answer is yes.
Yeah, me too. This is a lot of fun, and I'm really happy to share with everyone some of the things going on our campus. And yeah, I think this is a great way to share the wonderful community here at Soka University with the surrounding area. And so I'm happy to be a part of it.
Wonderful. Did you want to take more questions, or you have something else planned?
I think we could try one more question, and then yeah, we can maybe wrap up. So if you can find a last question.
What kinds of microfossils or biosignatures would you anticipate Perseverance would be likely to find?
Yeah, in the earlier Mars missions, the presence of these sort of hydrates were seen as possibilities of life, and it's not as if they'll find any intact life, because it's been so long that Mars has been dried out. But the presence of life over an extended period will leave behind precipitates that will be measurable. And so these would be compounds that would be sort of fused together in different microbial communities and then deposited in lake beds or in ocean beds over many thousands or even millions of years. So different types of complex hydrated materials would be my guess. So I'm noticing that Dan here has been playing around with the telescope with limited results in the beginning. Dan, I'm not sure, we're wrapping up here. Do you want to just show one of your favorite images that you took with our telescope recently?
Sure, as far as RGB or
Yeah, let's just do a color one just to kind of wrap up.
Okay.
And so this is actually not a live image from tonight, but this is an image that Dan took. Why don't you tell the story?
Well, this is an M33 image, and this is more of the pinwheel galaxy. And here we can see these galaxies have all these little spiral arms that are going out. And it's really interesting because as there's different in size and age, you can see how these galaxies kind of go from very clustered together to more having all of these arms go out. And it's a little bit hard to see here, but you can kind of see the arms going out and spiral out. So all these have different classifications, and that's something that we study here at Soka. But as it gets more and more clear, and as you get more and more information, you kind of start seeing all of these different aspects. It kind of reflect into the actual imaging that you're taking. So very interesting, at least for me.
Okay, that's really great, Daniel. Thanks for sharing that. And this galaxy, by the way, is 2.73 million light years away. So sometimes people ask me how far we can see with our telescope. And we can see anything, as close as the moon, just about a light second away. The Orion Nebula, about 1,500 light years away. Or this galaxy, which is the Pinwheel Galaxy, which is 2.7 million light years away. So that's a wonderful part of having a telescope, is you can use it to see the cosmos and actually look back in time as well. We're looking back 2.7 million years in this image. So I guess that's our program for tonight. I'm just really grateful to Renee and all the staff here at Soka University who made this possible. My whole team has been toiling away on this event for a while, and I'm just thrilled that we were able to do this for everyone. And so thanks everyone out there for coming. And we hope to see you at future events of this kind as we put more of these events together.
Thank you, Dr. Penprase. It was a wonderful, and we really appreciate it. Thank you so much. And we will put on more of these. It's wonderful. Thank you.
Yeah.
Thank you, everyone.
Great.